So, good morning, dear delegates of the Amsterdam International Water Week Conference. I welcome you to the first session of this morning, which is on treatment and monitoring of water. And let me introduce first myself. So I'm Huub Reinaerts. I'm professor in environment and water technology at Wageningen University in the Netherlands. And I'm happy to chair this meeting for you. And we have quite interesting topics, 3 topics to be presented. One is on clean water and ecosystem restoration, or one is on robust water characterization, and one is on real-time monitoring, and one is on electrochemical treatment of water. Quite a diverse set of topics, but very interesting to hear the stories that are behind this. And I'm glad I can announce to you the first speaker. And the first speaker is Siddhart Seshan from the Delft University of Technology and the KWR Water Research Institute in the Netherlands. And he's going to present his presentation on robust water characterization for the development of a biokinetic-artificial intelligence hybrid model to reduce nitrous oxide emissions. So Siddhart, please take the floor and present, and I'll be looking forward to hear what you have to tell. Please go ahead.
Thank you very much, Huub. I will share my screen now. Is it on presentation mode?
Yes.
Okay, thank you very much. Okay, good morning to all, and thank you for joining this session and to hear my presentation as well. The title of my presentation is the robust wastewater characterization for the development of a biokinetic AI hybrid model to reduce nitrous oxide emissions. And this research activities was done in collaboration with KWR Water Research Institute that I'm affiliated with, and with Waternet, the water company of Amsterdam, and TU Delft itself. So just to give a bit of a background, I would like to discuss the EU project, Horizon 2020 project called 5R for Water, which has supported this research activities and provided the funding as well. And within this Horizon 2020 project, the goal is to link the water sector to 5R, which is a smart data platform that is open source. And the goal is to demonstrate its non-intrusive integration into legacy systems and showcase how the interoperable capabilities and standardized interfaces of 5R can also be used within the water sector itself. So the idea is to build smart applications that we can use to do real-time analysis and analytics and manage our water systems going towards a digital water world, so to say. And there are some diverse partners as well within this project. The project has 4 demo cases throughout Europe, one in Greece, one in France, Netherlands, which is what I will be discussing on, and as well as in United Kingdom. And within Netherlands, it's led by Waternet. They're the demo case leaders, and we are working on the Amsterdam West wastewater treatment plant. So there it is. It's a large wastewater treatment plant. I'm sure many of you are also aware of this treatment process and system. And just to give a background on the wastewater treatment plant itself, it has a capacity of 1.1 million population equivalent, so it's quite large. It has 7 treatment lanes within the treatment system. The activated sludge process is a modified University of Cape Town process configuration. It's a unique plant as well because it also accepts external sludges from different wastewater treatment plants that are operated by Waternet as well. So it has to handle a lot more sludge than what is generated within the Amsterdam West itself. And to promote and allow the various research activities with various research goals, one treatment lane out of the 7 treatment lanes has been made available as a research lane by Waternet, where additional sensors are being deployed to be able to test new smart technologies such as AI, for example, and to see how we can meet our goals as such. And one such goal as well, which is within FireWare for water as well as for Waternet and us as a project team, is to try and achieve the operational control of wastewater treatment plants in near real time, potentially to reduce nitrous oxide emissions, which is a very harmful greenhouse gas. It has a global warming potential 298 times more than the CO2 equivalent. And as you can see on the right in the figure over here, there is in fact a considerable amount of nitrous oxide emissions that are also emitted from Amsterdam West wastewater treatment plant. And there's a strong seasonal variation as well, as you can see between the seasons. So in order to be able to achieve this aim, we are in the process of trying to calibrate a biokinetic model using the BioN ASDM model, along with it being coupled with the N2O model to predict the N2O emissions. And subsequently, there is also a scope to develop an AI model to predict the nitrous oxide emissions and be able to hybridize them and integrate them together towards a hybrid modeling format, which can then be used further to achieve our operational control and near real-time control goals and objectives. So just to move forward with respect to the biokinetic modeling, prior for us to be able to do any form of simulation, we need to ensure we have the adequate and necessary data to be able to input into the model itself. With respect to the characterization of the domestic wastewater of Amsterdam West, this was necessary to be able to acquire through a comprehensive and intensive sampling campaign. And this was conducted in July of this year for 8 days during one of those sweet spots between lockdowns and regulations that were there for the COVID pandemic. So we were lucky to try and find this window. And a flow proportional daily composite sampling was conducted for the raw influent and effluent wastewater to monitor certain key parameters such as COD, total filtered COD, same for the BOD as well, total TKN, ammonia, nitrate, and the phosphorus species, as well as the solids. The raw influent was also monitored for pH, alkalinity, calcium, and magnesium. And diurnal sampling was also conducted for the raw influent as well as the effluent specific to the research lane itself, so one of the 7 lanes. And grab samples were also conducted in various locations in the treatment process, such as the bioreactor units in the anaerobic and anoxic and aerobic zones, as well as the sludge treatment lines, which is quite important as well, and even the filtrate systems, which is also providing certain wastewater characteristics back into the activated sludge process. This is just to give an overview of the different locations that we tried to capture in our sampling campaign and monitor. So we had various locations from this aerial view shot of Amsterdam West. As we can see, there were quite a few locations in the sludge handling processes for grab samples, bioreactor units, the raw influent, and the effluent. And more importantly, in the bottom left corner, you could see the external sludges. So we had the external primary sludge and thickened sludges from different wastewater treatment plants, as well as waste activated sludge that is inputted. So we also had to monitor these sludge lines to be able to understand what we can input into our model. Here's also another overview of the different various parameters that we also monitored. So it is quite an extensive list where we try to take as many, try and understand our samples as much as possible, gather as much information as possible to allow us to be able to input and as well as cross-check the outputs that we get from our biokinetic model. Here's some figures on the raw influent wastewater from the sampling campaign. Barring some hiccups, which is bound to happen in a sampling campaign of this magnitude, where we did have some questionable values, for example, of the total suspended solids. As a whole, we believe that what we got is what we expected, and the data was sufficiently good enough for us to be able to perform the characterization of the wastewater specific to Amsterdam West, so that can allow us to conduct the modeling. Now that we have the data from the sampling campaign, we can now do some modeling using the BioWin ASDM model. The sampling data, as I mentioned, was used to characterize the common quality parameters such as COD, TK, and TP into their fractions. So now we have a list of the wastewater fractions that can now specifically be entered into BioWin that are specific and unique to Amsterdam West, the domestic wastewater of Amsterdam West, to be more precise. The grab samples of the sludge lines were also used as input into the model, for example, in the external sludges. And it also was used to perform sanity checks throughout the sludge lines to ensure that the model outputs that we were getting from the simulations are somewhat in the range of what is actually what we see in the ground. Of course, the dimensions of the process units were also inputted for the treatment lane. The recycled flow rates, so the MLSS recycles, as we can see over here, the NOx recycles, typical recycles that you have in an MUCT platform process configuration was also inputted. The liquid temperature was also inputted that allowed us to do season-based simulations. So we started off with doing the summer season to be able to ensure our model provides a good fit in that. And then we subsequently move to different seasons as well. And we started off with doing steady state simulations, as is the practice prior to going forward with dynamic simulations. The recycled flow rates and the liquid temperature, for example, were inputted using online sensor data that is available in Waternet system for the research link. Here are some first results of the steady state simulation that we did with the BioWin model. So as I mentioned, the steady state simulations were conducted seasonally using historical laboratory measurements for the calibration process. And we did observe a good fit with respect to the observed data and our model predictions for the different various variables of the effluent for the summer season. So this gives us confidence to know that our sampling campaign has provided us adequate data for the characterization of the wastewater, which we can now use further to conduct the simulations of steady state and dynamic for various seasons moving forward. To wrap up, just to give an outlook on the sampling campaign itself. So we did conduct 8 days of sampling, and this was to somehow be able to balance the costs that we would incur if we try and go for too long, but at the same time be able to collect sufficient amount of data and information for us to have meaningful understanding of the wastewater that we do have in Amsterdam West. Additionally, we try to increase the data redundancies by focusing on various samples and locations so that in case there are some unforeseen situations that we do arise, such as a pandemic, for example, we do have sufficient data points to still be continuing with the analysis. And Amsterdam West is a rather large plant with a lot of complexity with the external sludges, and also a monitoring campaign of this magnitude was rather time consuming and complex, but that was a great learning as well to try and have some form of understanding and framework on how we can do such a monitoring campaign. But the primary goal of characterizing the raw influent, the quality parameter of the raw influent with the fractions was achieved, and this was allowing us to be able to map it in the BioWin model as well. And some future modeling activities, we will now move forward and continue doing steady state simulations for other seasons, and also continue with dynamic simulations using online sensor data now that we have the wastewater fractions. And such biokinetic model that is being calibrated is a prelude to be also calibrated on N2O, nitrous oxide sensor data, and which will also be followed by AI modeling of N2O predictions. And then finally, investigations will be conducted on how to hybridize these models. That's it from my side. Thank you very much, and happy to take any questions.
Thank you very much, Siddhart, for your interesting presentation. And I would like to invite the audience to put questions in the Q&A. I don't see any questions yet, but please go and take your opportunity. We still have some time to have some questions. So I have a first question myself, Siddhart. So I think it's very interesting, this hybrid model.
Yeah.
But can you also indicate what you expect as the crucial parameters to control or to reduce the N2O emissions? What is your assumption prior to do all this modeling? What would be your guess? What would be crucial parameters?
Yes, I think, very nice question, Huub. And in fact, what literature has suggested and what we are seeing is that dissolved oxygen, for example, is a very important operational parameter, particularly the DO levels that we do see in the aerobic zones as well as the anoxic zones, because that sort of give us an indication on which production pathway of the N2Os are active. So the controlling of DO and understanding the DO levels and the changing of it with respect to N2O production is a very key parameter to be able to try and control and also test these strategies with our biokinetic model. So I would say that's a number one. But after that, there are also, of course, other things that have been sort of sporadically mentioned in literature. Let's say, with, for example, the pH of the mixed liquor, sludge retention time, and all that. But I think DO is your number one go-to before you can start considering the rest. Yeah.
Yeah, so then you predict that in fact the transition from the oxidation part of the treatment and the denitrification or the nitrification part,
yeah,
and maybe also the denitrification is crucial. So you have to very sharp treatment conditions with respect to oxygen, to limit the N2O emissions.
Absolutely, yes.
Yeah. Okay, I don't see another question yet. Please use the Q&A if you have any questions, not the chat, but the Q&A, please. Let me check whether there is something in the chat. I don't see yet. Maybe another question. So you have, of course, N2O as one of the greenhouse gas emissions, but you have also, of course, methane and CO2. Yeah. So you have the three major greenhouse emissions from wastewater treatment plants. Yeah.
Yes.
Do you foresee that your hybrid model can be expanded to all the greenhouse components?
Yes, I think so, because at least the biokinetic models are, of course, mass balance based. So you do have to account for this, of course, when you add the complexities for the other greenhouse gases as well. A very unique thing about Amsterdam West and what Waternet have done over there is they are also, in fact, measuring the methane and the CO2 in the off gas. So there is data available to also extend past the N2O. But I think N2O is considered, of course, the most potent one to start with. And then it will naturally be extended. I think there is scope for that, and as well also the indirect carbon footprint from the energy consumption as well. So this is also another important thing. Yeah.
Okay. So apparently, it's for the people in the session still a bit early to raise questions. So thank you very much, Siddhart.
Thank you very much
for your nice presentation.
Yeah.
And then we continue with the next presenter, and that is Marjan Joris. She's from a company iFLUX, and she's going to present about real-time monitoring of groundwater flux and that creates insight in the complex water system of a case Romboutswerve Polder in Damme in Belgium. So, Marjan, please go ahead and take the floor to present your story.
Okay, thank you, Huub. Hi, good morning, everybody. I will first try to share my screen. So, if it's all right, you can all see my screen right now. Okay.
Yes.
Perfect. Yes, so again, thank you for having me here and thank you for joining the session. I'd like to tell a little bit more about our monitoring network, where we measure also horizontal and vertical groundwater flow velocity and direction. And these measurements provide new insights in the water system of the Romboutswerve Polder in Belgium. The Romboutswerve Polder is an old polder or reclaimed land, and it's limited by canals and crossed by different waterways. Although the canals can feed the waterways even in summer, drought is a problem in this area. Because of the low water levels, quality of the water can be poor, and the growth of blue algae do not allow to take in the water of the canal at all times. And we expect, due to the climate change, temperature rises and there will be longer periods of drought. On the other hand, during heavy rainfall, water must be drained to prevent flooding in the upper urban areas, in the city of Damme, as well as the city of Bruges. And also due of climate change, we expect increase in events with high to even extreme precipitations. So the possibilities to retain water in the area are limited. And at the moment, the water system is disturbed, and even in winter, there are hardly any puddle and swim conditions, which is crucial for the meadow birds, and the population of these birds are drastically decreasing. To counteract the effects of drought, the aim is to raise the water level, although more is needed to come to a sustainable water management that's optimal attuned to nature, but also agriculture, and to prevent or to avoid flooding in the urban areas. The aim is to optimize the water management in the Romboutswerve Polder, tackling the challenges of drought and flood, realize a climate-robust and optimally functioning water system in connection with agriculture land use, conserve biodiversity and water experience, promote good water quality as a precondition for top international nature and as an indicator for sustainable agriculture management, preserve the cultural historical landscape, and promote added value through smarter management and exploitation in a climate-robust and biodiverse way. So the pilot monitoring network helps to collect and exchange knowledge about the complex water system. Where in the past, monitoring was limited to measuring the effects at the surface, we want to visualize what's happening in the underground by measuring the groundwater flows and exchange at the interfaces, the interfaces of ground and surface water, but also of precipitation that goes through the groundwater, etc. By monitoring, we like to organize a collaboration of partners and an interactive project approach with various stakeholders. The focus is on differentiated water level management and innovative water retention and infiltration initiatives, distinguished in design, technology, and the target audience. With iFLUX, we provide real-time data of groundwater and contamination flux. It all started a while ago, in around 2070, with a PhD about spreading of contamination in groundwater. It's a PhD of our founder, Guy Leverret. And out of that PhD, iFLUX was born. When in 2070, we entered the market with a modular, scalable cartridge sampling system. I take my pen, voila. It's this one. With this cartridge system, we can measure almost 130 types of contaminants, and it makes it possible to determine the flux of the pollution and the groundwater at very low detection ranges. We have done more than 100 projects investigating the fate and behavior of contamination in the groundwater. And based on this experience and the questions of our customers, we developed a digital smart groundwater sensing probe, including a unique sensor flow chip inside. We are able to measure continuous groundwater flow rates. We measure specific low-flow groundwater ranges down to the centimeter scale a day, typical to Flanders, but also to the Netherlands and other low and the typical low flows in groundwater. By adding smart data layers and learning algorithms by a smart groundwater management platform, we show our customers the groundwater dynamics in an online dashboard to ensure the compliance and integrity of the water system. So Here you see our vertical sensor probe. In the sensor probe, there is a microfluid chip with a small sensor capillary measuring flow velocity based on temperature in a closed well system. Oh, sorry, I go back. The sensor is built in a probe, and the probe is provided of, there's 2 filter areas, and it's provided of a fine mesh to prevent clogging. And the probe can be installed directly in soil or in a specific well, allowing to measure the vertical flow. Here you see our probe for measuring horizontal groundwater flow. These are the meshes where the groundwater flows in, and if we open it, you can see there are 2 sensors perpendicular to each other, and those 2 sensors allows to measure the flow velocity, but also based on the vector sum, the direction is determined. And this probe, as you can see, voila. Okay, and this probe is installed in a well. For the best results, we prefer to use our own special designed pre-pack filter, because it's by that way the flow is controlled optimally controlled. Okay. To determine the flux in the aquifer, the sensor measurement is conversed based on the characteristics, the conductivity of the aquifer, the well, and the probe. A correction factor is calculated, and herefore control lab tests are executed in a sandbox. And because of the limitation of lab setups, additional CFD simulation are done in our digital lab. And to come back to the pilot in Damme, together with Natuurpunt and the University of Antwerp, we set up a first monitoring network to create a better understanding of the water system to restore wet grassland and swamp forest, preserving and restoring biotopes. Herefore, we installed a meteo station and 5 pressure divers and a CTD sensors, a horizontal and vertical flux probe, and all data are sent to a real-time dashboard. Here you see the Romboutswerve, where we installed the vertical sensor in, and in the bank we installed a well with a probe for measuring horizontal flow velocity and direction. The dashboard, where you can see we have we combine the groundwater level measurements together with temperature and conductivity, and we measure those in the different wells in the area, and we also have the vertical flux and horizontal flux. Here you can see the magnitude and direction, and the direction is also indicated on this circle as well. We combine those data with the information of the weather station, measuring solar radiation, wind, humidity, and precipitation, and we combine our own measurements with available data of level measurements in the water base, which we download from waterinfo.be. So, and then let's come to the first finding of our pilot test. We see a variation in flow velocity and also in direction. Okay, it's not a surprise, of course, but in contradiction with the expected, the change is not directly related to the tide, of not only related to the tide. We see only one change in direction a day. When it's related to the tide, we would expect more changes a day. It's more a day-night related change. Further investigation is needed to find out if there is influence of the evapotranspiration or maybe the nearby canals. We also see that with the change in direction, the vertical flow respectively increases and decreases. Okay. And we see that, okay. And here you can see there is for the vertical flow, there is an increase and decrease of the, but we see there is always a very strong natural exfiltration. We notice now that this natural exfiltration, it's much higher than the water artificial discharge supplied by pumping. The exfiltration is clearly correlated with the precipitation. You see precipitation, and we see an increase in the vertical flow, and also correlated with the measured groundwater levels on site. And we see that the changes in the vertical flow are very similar to the level variation in a canal further away, where water is discharged to keep the water level high. It's in the Damme Leopold canal. We can see it here. While we don't see the variation in the nearby canals, here in the Canal Brugge-Sluis or in the Romboutswerve, we don't see the variations. So the seepage from the canal Leopold's Canal to the Romboutswerve Polder should be further investigated. So that were the first findings of our pilot testing. I thank you for your attention. If you have more questions, you can reach me at this email address, or you can visit us at the AIWWW conference as well.
Thank you very much, Marjan, for your nice presentation on a polder in Belgium. I would again invite the audience to raise any questions if you have for Marjan. At the moment, there are no questions yet. So, but I have a question to start the discussion. So you are completely oriented with your sensoring on water quantity, yeah? So the water quantity flow modeling of the system. Do you envision also that these sensors can be expanded to sensors that are also able to pick up water quality parameters like salinity and nitrogen and phosphorus, because these are the important parameters for the ecological and agricultural quality of the system. So
yeah, sure. Sorry. I have a strange noise. Okay, yeah, I'm sure that's possible. Actually, we now have a project where we already are measuring the nitrate concentrations in real time. And for the other parameter, I have to say that we are not developing the sensors by our own, so we're using existing sensors. But at the moment, there are not really good sensors available yet that we can use. But when there are, we will try to integrate them in our monitoring network as well. Yes, that's true. Of course, we are already measuring conductivity, pH, temperature, etc. We can all measure. We already include them in our monitoring sensor network at the moment. But for the more and nitrates as well. But for the phosphates, for the other parameters, we're still looking for the good sensors that we can use at acceptable costs. Yes.
Yeah. Okay. Thank you. And then maybe another question is, so you do this online real-time monitoring, but that's also in service of the water management in the polder area. So by the, I think the water board or the water management organization. And can you tell me a bit how that then works? For instance, if the farmers want to use the land and go onto the land, how does your online real-time monitoring help them, the water management, to operate all kind of actions in the polder on a daily basis? Yeah.
Actually, now we just started with the first pilot test. That is the first pilot test I presented now. But indeed, we are working to make a bigger project out of it, and it's our goal to have more measurements, because now it's still very limited to a certain point, but we need to know more. But and we see that at the moment there are a lot of there are some things done to higher the water level in the area without having any hinder for the other stakeholders. But we see that the system is not yet known enough, and which it gives some troubles over there. So it's good to know the system better, so we know what's good for all different parties in that way. So we can better control the water system and showing the advantages to the different stakeholders. Yeah.
Okay. Well, Marjan, I don't see any other questions coming from the audience yet. So I would like to thank you for your presentation, and then we go to the last speaker of today in this session, and that is Christian Linnartz from Germany, from the University of Aachen, in their group of Matthias Wesseling, and he's going to present a story about flow-electrode capacitive deionization from lab to application. So Christian, please go ahead and present.
All right, so thank you very much for the introduction. Now I start sharing my screen. And then you should see it from the beginning. And if that's fine and you can hear me. Yeah, I'd like to thank you all again. Thank you for having me here. I'd like to give you a story today about flow-electrode capacitive deionization. So a little bit more to the end story. We're not talking more about the water, but I'd like to shift the focus here a little bit more to what is in the water and if that's a real valuable system. And this called flow-electrode capacitive deionization, a technology we developed in Aachen 6 years before. And now we worked on this quite a long time and trying to get this into industry. And I'd like to show you what we're working on. First thing is, what is the target? What are we searching for? So in most cases, we're talking about sewage plants. And then the question is, why do we have a sewage plant? Because there are emissions of several ions, for example, sulfate, nitrate. We talked about phosphate now. So these are all ions. But these ions also have a value to the industry because they use that usually in, for example, acidic processes. And the question is now, how can we feedback those? And sometimes you want also not just feedback those ions, but you want also to select the ions. So separate between sulfate and nitrate, for example, in these conditions. And then there is usually, when you do this, it should be energy efficient, as we all know, because that's what drives our industry. And we need this kind of selectivity in the system, in the black box I'm shown here, to separate, for example, the nitrate and give it back selectively. And, for example, then go with the sulfate in a separate step or give it anyways to the environment or to another industry. That's also a thing which should be usually done at ambient temperature. That's usually a reason due to the cost for high temperature systems, and it also should be with no pressure, which in the specific case we have an industry project on biosecurity regulation. When we think about that, we need to not just think about selectivity and energy efficiency, but we also need to think about robustness. We were talking about now the big plants before, and you all know that when we work on such a system, it's not just being in the lab, it should also be going in the industry, and there it should run like in a sewage plant for years and years, and should be stable for a lot of time. Then what we always want is a high water recovery rate, so that we can harvest most of the system we have, which also goes hand in hand with a wide salinity range. So our target is now to go from very low diluted wastewater streams, take back the valuable salt and concentrate it as high as possible so it can be easily reused as a feed for an industry process. And that's a key factor here, the whole system should be continuous. So it runs as the industry goes on a flat curve forever and ever. So how does this system actually works like? So what we do is this flow-electrode capacitive deionization. We have an ion, we have a salt solution consisting of ions in an electric field presented by two outer current collectors. We also introduce ion exchange membranes. That's where our basic knowledge of the chair I'm from is coming from. And then we also introduce on the outside what we call a flow electrode. And this flow electrode is basically a solution of activated porous, activated carbons with a huge surface area in a water solution. And then when we apply the potential, those ions move towards the counter electrode, respectively, a system which you all know from any other ion exchange membrane process with electric fields. However, what happens then is that those particles actually get into contact with the outer electrodes. They get charged themselves, and thus the ions absorb to those particles. So we end up with two streams, or three streams basically. One stream with the desalinated water, and then we have one stream where there is a flow electrode just charged with cations, and then there is a flow electrode where just anions are there. So that's also a uniqueness to this process. So we can start thinking about mixing several systems and several ions and reversing this. And when I'm talking about reversing, that's actually done in a similar system by just reversing the outer potential, and thus the ions are forced back to the inner channel, and we get a concentrated solution. So that's actually shown here on the left, where we see schematically those two modules. We go from a feed to a dilute, and we also go from a feed to a concentrate solution. And on the right, you can see a typical system where we here did it as an example for sodium chloride. Most of you know and have numbers with that. And we have a feed solution here, for example, 60 grams per liter, typical industry waste solution. And then we want to go to a dilute, which is low as 3.5 grams per liter. But at the same time, we can also concentrate in a very single step to, let's say, 250 grams per liter in the concentrate, or even higher, depending on the system. How do we do this? We do this by changing the flow rates here. And having the concentrated flow rate lower, we get a really high concentrated stream here, which also means that we can get to water recovery rates, which are at 80 or 90%, as we shift those salts and not to water levels with it. So that's a unique feature of the system. And when we're not talking about concentration, we also need to talk about the energy efficiency again. And energy efficiency is shown here. There is a thermodynamic minimum for separating salts. Then there is a line where we work our system, usually at 1.2 volts as driving force. And then we know when we reduce the potential, we get a window, so to say, for lower systems. And then we see with the stars here that we actually meet what the theory says with experiments. When we now compare this, for example, for reverse osmosis, you see that the energy demand is far, far lower. However, reverse osmosis is usually not capable to treat such high salinity concentrations in a very simple step. When we now compare it to a system which is usually used for higher concentration, like evaporation or compression technology, then again, we're a little worse. However, we still have a possibility to further reduce the potential driving force. That's where we get like in the same range as the system here. And we can also prove this with experiments. So that's why we are competitive here. So we are selective, we are energy comparable and comparable in energy demand to evaporation systems. And that's why we were thinking about how to move on. One key factor now of this whole system is actually what happens now here in the lower part, where you can see that there is some interaction needed. And that's just a key system here that we get energy in terms of electrons and absorption of ions in a very good manner, which is making the system more efficient. And that's where we went okay thinking, now turning this diagram 90 degrees. We have two pathways, one pathway for the electrons, one pathway for the ions in this very simple channel. This separates the two layers. And we thought about, can we go this a little bit smaller and go for membrane electrode assemblies, where we actually apply a conductive layer here of a carbon fabric on top of the ion exchange membrane directly, and create what I call a single point of contact, where I get ion absorption and electron transfer at the very same spot. This also gives us new opportunities for the housing, which might be now non-conductive and flexible. And that's actually what we started to produce and also published and patented. So we make now this membranes. We can see also that it works actually as a functional reinforcement. So even when the membrane swells, it doesn't detach. It's long time stable. It gives a certain strength to the material. And then we usually need to apply a sealing on the outer side. You can see this now from the front and back side, and also a detailed view here, where we have feeding solution, and then it goes basically in plate and frame modules, as most of you know. And then one further step is we're not stuck with this size, which you can see here, which is 40 square centimeters membrane area, but we can also now produce a membrane area of 320 square centimeters, which is now our standard size. And knowing all that, we're now stacking plate and frame modules to get a larger system. So a little bit coming to the conclusion, I hopefully showed you that we did a lot of basic research on this technology. Today, I talked a little bit more about the application side. There is many applications we're targeting for, which you can see and maybe read in our publications. Applications should be in any kinds of recycling of valuable salts. And we are, for example, working now on lithium recovery in one project. We are working on treating of wastewater, high solid salinity wastewater from dye industry, textile industry, basically here. And then we also go for industry scale system with German chemical or steel industry, and 2 big projects which are funded by the German government. And this all together brings us to design the module, which I was just talking about. So this is basically the 320 size module. You can see the plate and flame systems here with the blue spacers in between. That's actually what we're harvesting for, what we're going for, and what we are piloting in the next year. And since we are now working so far, and it says from lab to application, we also want to convey this now into a startup company. And we call this system now Amovion. And you can search for it online. And you can also see, if you're in Amsterdam this week, drop by at us on the Aquatech. If you join this conference also in presence, maybe you have a time and drop by our booth. And let's talk about this, and let's talk about FCDI and what your suggestions to it would be. With this, I'd like to thank you for your attention and looking forward for questions and any suggestions. Thank you.
Thank you very much, Christian, for your presentation and interesting technology. So is there anybody in the audience that wants to raise a question for Christian? Please take your opportunity. We have quite some time to raise questions. So if you have a question for Christian, take the opportunity in the Q&A. I personally, I have a couple of questions, because my own group also works on capacitive deionization and related technologies. So one question is about one of the problems we have in CDI is that the electrode materials, the porous electrode materials, seems to erode a bit over time, and that makes the lifetime of the technology in normal CDIs always an issue. Do you think that with your flow approach of you have solved that problem, so that you can refresh, in fact, the electrode materials and don't have this problem anymore?
Right. So that's actually what we think. That's a beneficial part of this flow system, that we go with a continuous system, that we charge those materials. And you're totally right. So when we discharge and charge, as you do this in CDI, that some of this material erodes. Another thing we need to take a little bit more care of is that when the particles actually have contact, a lot of contact, there is abrasion, the particles get slower, rheology might change. That's a little more hurdle. But the moment this is too big, or rheology density, viscosity is too high, we can simply change the flow electrode, which is a very cheap system. Activated carbon is cheap, water is cheap. And we can do this without dismantling the whole module, which you would rather do in CDI, right? So in CDI, you have the static electrodes. You need to separate all the system and put in new modules. And we simply, changing pump directions, have a new flow electrode in there. And then the module is still, again, in a state where like it was on the first day.
Yeah. Okay, so thank you. Then another question is that you showed your graph on the concentrations of salts and the efficiency, the energy efficiency of the technology. So my question is is your approach especially suitable for concentrates? So already very concentrated solutions. So maybe the brines and the concentrates that are already from a pre-treatment with RO or another technology, or can your system also function for more dilute systems? So for instance, brackish water or low salt concentration systems. What is your opinion about that?
Okay, thank you very much for that question. That's a very important question. I always think that there is two different regimes I like to separate now. There is the regime in the center where reverse osmosis is very, very strong, and which is like this 30 grams per liter sodium chloride solution, seawater, what we all know. In lower system, it might be more energetic efficient to simply remove the ions. So to spend an electron for each ions, and you have to pay those electrons basically. So it's more energy efficient. As you know, from the CDI technologies you're also working on, the same is also true for the FCDI system. So definitely, yes, from an energetic point of view, we can work in this very low concentrations. However, there's also the second part, which is like in the concentrations above the reverse osmosis, or which would be usually a concentration of a concentrate stream of a reverse osmosis plant, where reverse osmosis is due to scaling just not capable of concentrating it any further, and it's anyways also not capable of separating ions by any charge difference or size difference or so. And this actually also, for example, nanofiltration or any other pressure-driven system has this problem of scaling. And when you use now a electric system, you don't have scaling anymore, and you have selectivity. So maybe we can think about that using our system at this spot, even though it might be not that energy efficient comparing to a reverse osmosis plant, but we can do something more. We don't have scaling. We don't have selectivity. We have selectivity here as a solution. And yes, so the answer to the second part is we definitely think about using this system also as going for a zero brine system, concentrating the brine further.
Yeah, so the FCDI technology can have then basically two positions in a treatment scheme. It can be a standalone technology, a little bit for maybe more dilute systems, and it can be part of a technology train for more concentrated streams to accommodate recovery and reuse of all kind of metal or ion species in the system.
That's true.
Yeah. So still no questions from the audience. So there is one first question. So so it's by Tanya Chauhan. What are the possibilities of using other materials for making a cation exchange membrane apart from activated carbon?
Okay.
Do you understand the question, Christian?
Yeah, I do understand the question. However, I have to maybe answer as such. So the cation exchange membrane is not made from activated carbon. So there is still a polymeric cation exchange membrane which we use. However, the slurry, the particles in the slurry, or in the flow electrode, as we call it, are made from activated carbon. And yes, you're right. We can use in both places different systems, so we can have different membranes. We went also with nanofiltration membranes and so on and so forth to tune selectivity here. So that's the membrane part. And then, for example, we have a system where it goes into medical treatment. I leave it like this. And in this environment, activated carbon is not a good system. So we can also have other materials here, any kind of metals, catalytic particles, such as this. We also tried this, as it actually works, and it gives some beneficial part. For example, if you want to separate a salt from a system and then directly do a catalytic reaction in the second step, in the second module, you can have different particles here. However, when we're targeting these big systems, like in the industry, we want to have a particle which is cheap, which is electroconductive, where you can buy tons and tons of materials and they are all the same. And that's why our main focus for company-wise is now on the activated carbon, but the research goes on with other particles.
Okay. Well, thank you, Christian, for your interesting presentation and nice discussion we had. We are now ending or coming close to the end of the session, and it's my honor and duty to sum up a bit what we discussed today. So let's start with Christian. So Christian, you in fact came with a new electrochemical electromembrane technology to contribute to resource recovery. So making materials available in a kind of circular economy approach, I think very promising technology. If I then go to the first presentation of Siddhart, showing the hybrid models it can be used to, in fact, to analyze and re-engineer wastewater treatment plants to reduce greenhouse gas emissions. So, for instance, nitrous dioxide, so N2O, or maybe also methane, and maybe even CO2. So to re-engineer our wastewater treatment plants in a way that they don't emit that much greenhouse gas emissions. In this way, we contribute with your presentation to the challenge, the global challenge to mitigate climate change, which is now in Glasgow, the big conference, of the world leaders. So we contributed in this session to that. And then with Marjan Joris, her presentation, we were working, have been presenting on the water management of polder areas, nature reserve areas, how to mitigate the water, to manage the water in the system in a way that the climate change effects like peat oxidation or the natural and ecological functioning of the system is preserved. So also there we contributed to the more ecosystem functioning. So in this session, we dealt with three major areas of challenges we have to deal with in our environmental and water management approach. And I think it was very interesting. And I would like to thank you, presenters, for contributing to this session, and the audience for being listening and also raising at least 2 questions. So thank you very much, and see you around in the other sessions of this conference. Thank you. Bye-bye.
Thank you. Bye.